Hey, well, welcome everybody. I appreciate you being here. Today we're going to talk about radiation production, how X-rays are made. Should be a little more interesting than it has been. So first, we're just going to go through some vocabulary that's involved with radiation production, and then we will actually run through the X-ray tube, and I'll talk to you about how X-rays are produced. So I'm just going to go ahead and switch screens here. And if anybody's listening, just let me know if you can't hear me or can hear me. Oops. Okay. I hope everybody can see this. So let's get started. Welcome to the LSRT study group number 5. X-ray physics and production. A little bit of physics, mostly production, but they kind of go hand in hand. So let's just run through some vocabulary real quick. So anode is the positive charge electrode in the X-ray tube. Charged electron, it attracts charged electrons from the cathode. So the cathode is the negatively charged electrode that produces electrons via heat. So that's going to be very important. It actually produces negatively charged electrons from extreme heat. And we'll talk about how that works as well. Filament. The filament is a thin coiled wire that emits electrons. Okay, it's part of the cathode. So the anode stem is a connecting piece. It holds the anode plate, and it's usually made out of molybdenum, and it helps dissipate heat. The rotor is the copper component attached to the anode plate, and it spins really fast, about 3,000 revolutions per minute, which is really moving. The stator is the electric motor that uses electric magnetics, creating a magnetic field that rotates the rotor. Kind of cool. And when we get into the meat and potatoes of it, you'll see what that is. So tungsten, molybdenum, and rhodium. These are metals with a very high melting point. And they are all, well, not in different X-ray machines, different metals are used. The primary metal is actually tungsten, but the other two can be used as well. And it does affect the type of X-rays and the strength of X-rays that are produced. Like I say, they are the anode plate, the filament, and the anode stem. So focal spot. This is the area of the X-ray tube. It's part of the anode where X-rays are produced, and we'll talk about that more. The tungsten plate is part of the anode as well. So tungsten, we already know, is a metal with a very high melting point and density. Vacuum means completely void of gas. Thermionic emission, we'll talk a little bit about that as well. It's the process of releasing electrons from the metal coil when heated to a high temperature. Now, these are all just vocabulary words that you're going to have to be familiar with. So electrons are tiny charged subatomic particles that orbit the nucleus of an atom. Focusing cup. The metal cup on the cathode which focuses the stream of electrons onto the anode plate. Okay, so the enclosure is glass, Pyrex. I don't know if you guys are aware of Corningware. It's really, really hard glass. The patent is actually owned by the Pentagon for Corningware. And yeah, it's just a really, really hard glass. You can drop it off anything and it's not going to break. So there's a really strong glass around the components of the X-ray tube. Ball bearings, we'll talk about those. They're steel plated, rolling, uh, lubricated, that supports the rotating anode and has a high thermal stability. Okay, so target interactions, there's two types of radiation that are produced uh, at the anode. One of them is called Bremsstrahlung. You know, it's kind of a funny word. It's a German word. It actually means breaking radiation. Brems means breaking, and Strahlung means radiation. So breaking radiation. Electromagnetic radiation emitted when a charged electron loses kinetic energy due to an interaction with another charged particles, colliding with the nucleus with the maximum energy created a X-ray photon. We'll talk a little bit more about that. But so Bremsstrahlung and characteristic is the other type of radiation that is produced at the anode. Characteristic is a type of electromagnetic radiation emitted when an electron from a higher energy level fills the vacancy in a lower energy level. So an electron transitions with the atom. This creates a discrete X-ray photon with a specific energy level. This occurs when an incoming electron collides with an inner electron, knocking it out, leaving a vacancy to be filled by an electron from a higher level. It's just physics. I don't know if you guys remember from high school physics, but it's kind of the same thing going on here. So Bremsstrahlung is a result of an electron deceleration, which is a huge part of how X-rays are formed. There's a rapid deceleration, which causes a reaction, and electrons are turned into X-ray photons. So, well, characteristic radiation is a result of electron transitioning within an atom. Okay. So Bremsstrahlung produces a continuous spectrum of energies, whereas characteristic radiation produces a line spectrum with distinct peaks corresponding to the energy levels of the target atom. Okay. So basically, is what you need to know is Bremsstrahlung is more intense and more predominant. So most of the X-rays that are formed are Bremsstrahlung X-rays, where some of them are characteristic X-rays, which are a little bit weaker, not as predominant. So, all right. So let's look at these a little bit. So this is characteristic radiation, and you'll understand this a little bit better when we run through what the actual X-ray tube does. But you've got incoming electrons right here, okay? And it actually hits an electron in the outer or the inner shell of the atom and knocks that out. And when that knocks that out, it's turned into a lower energy X-ray. So, and they're knocked out in different directions. So as what happens is one of the outer shell electrons goes down and takes its place, okay? And what you need to understand about characteristic X-ray production is basically that characteristic is a lower energy X-ray photon, basically, and it's not as predominant, okay? We're not gonna get too deep into that. So Bremsstrahlung is the more predominant and intense X-ray photon that's formed. So here we've got an incoming negatively charged electron. So as what happens with Bremsstrahlung is it goes near or hits the nucleus of the atom, okay? So the further away it goes, it's going to be less of a 90-degree angle here. So it's going to come out down like this, okay? And when it gets close to the nucleus, it's going to make a sharp turn and go up. And when it hits the nucleus, it's actually going to go straight up. So is what you need to know about this is that the closer it is to the electron, the more energy it's given out. So if it hits the electron, you're going to get the most energy out of that X-ray photon, okay? And that's kind of what you need to know about the two of them. Is the characteristic is actually going to hit one of the electrons, okay, and knock it out of the shell, and it's replaced by an outer shell electron. So, and it's lower energy. Bremsstrahlung, it actually goes near or hits the nucleus, and depending on how close or if it hits is going to determine whether or not it's a higher energy X-ray emission. So we're just trying to break it down into as simple as we can. I mean, there's lots of things we could go into here, but I don't feel like you guys need to really know that. Just be familiar what Bremsstrahlung and what characteristic are, okay? Okay, so when you look at your X-ray machine, this is the actual X-ray tube housing. It's lead-lined metal. The reason it's lead-lined is because when the interaction happens at the anode, it forces X-ray photons everywhere. So it needs to have a way to protect us from those radiation waves. So that's the X-ray tube right there. Okay, you can see where the electric goes in here. This is negative. This is positive. So we know that the negative is the cathode and the positive side is the anode. Okay. All right, here's an actual X-ray tube. You can see that it's enclosed in glass, right? This really hard refined glass. Okay. This side right here is the cathode. Okay, you can see right here where the filament is. And this side is the anode. This is the anode stem, okay, and the rotor. So rotor, anode stem, and this right here is the anode plate, okay. And you'll note that it is beveled a little bit right there, but that's done for a reason. It's going to direct those X-rays right into the collimator box, okay. And we'll talk more about that in a minute. Kind of neat looking though. Okay, so this is the tungsten filament. This is where all the heat is generated, and this is where thermionic emission happens. The coils are heated to an extreme temperature to the point where they boil off negatively charged electrons. It causes an electron cloud. We'll talk more about that in a minute. But anyway, our machines only have one. Okay, one filament. This has two filaments, but our machines only have one. But that's what the tungsten filament looks like. All right, so this is my cool drawing. I know that my art skills aren't good, and I apologize for that. But I think that it'll serve the purpose of so that you guys can understand how X-rays are produced. Okay. All right, so you go back, you see this right here, right? Okay. Okay, and that's what this is right here. My drawing isn't as good as that picture, but that's okay. So over here, we've got the cathode. Okay, the cathode is negatively charged. Right here, we've got the anode. Okay, so let's start from the beginning here. So the X-ray circuit wall current, which is AC, which is alternating current, is changed to DC, which is direct current. Okay, it hits a step-up generator. That's that box that you see in your X-ray room, and it actually steps up the voltage before it hits the X-ray tube. So we're getting a lot of electricity coming in here. Okay, so what it's going to do, the electricity is going to come in here and it's going to heat that cathode or the filament right here. It's going to heat it to an extreme temperature. And we know that tungsten has a high boiling point, so it can withstand these high temperatures, and that's why it's made out of tungsten. So what happens is it's heated up right here, this filament, and it starts boiling off negatively charged electrons right here. So this right here is what's called an electron cloud. Okay, So we know that the anode over here is positively charged, so it actually attracts the electrons over to the anode plate, which is right here, or the focal spot. Okay, so these electrons start moving across there. I should note that there is a focusing cup right here, and it helps focus the electrons towards the anode. Okay, so the electrons are traveling across the X-ray tube, and they actually hit the anode plate right here, or the focal spot, or the target, the anode target, that black little thing right there. And so what happens is there's a rapid deceleration, and that's when the electrons hit the atoms of the anode, and we get either Bremsstrahlung radiation or we get characteristic radiation. And the characteristic radiation really kind of depends on the type of metal, whether it be molybdenum, rhodium, or tungsten, primarily tungsten. And then, like I said before, most of the X-rays that are emitted are Bremsstrahlung X-rays, photons. Okay, so rapid deceleration hits the tungsten plate at the focal spot, an interaction takes place, and X-rays are formed, whether they be Bremsstrahlung or characteristic. Okay, now we know that X-rays are going to go all over the place. Okay, but we have X-rays that are filtered down into the collimator window, right? And there's filtration inside the collimator window. And as what the filtration does is it takes away, or it eliminates the weak X-ray photons, okay? So once those X-ray photons hit the collimator, we're getting good X-rays coming down to the bottom to the image receptor right here, okay? Now, let's go through some of the parts. I hope you understand kind of what I'm saying there. Is all you need to know is there's a filament that's heated up. Negatively charged electrons are emitted from that filament. And due to tube potential, they are moved across the tube to the anode plate, okay, where they are converted to X-ray photons. And I'll add right now that only 1% of the electrons that go across to the anode plate are converted to X-ray photons. 99 point something % of the electrons are actually emitted as heat. So, and now the X-ray tube around the glass plate right here, it's all filled with oil, okay? And as what that does is that helps dissipate heat. So we can get rid of that heat somehow. So I did mention in the vocabulary that the glass tube that houses the cathode and the anode is completely void of any type of gas or air. So if you were to shrink yourself and go inside the tube or the glass housing, you'd probably implode because it's kind of like going into deep space. There's just no air in there, okay? Very important that you know that. So let's go over here to the rotor. Now this hot dog looking thing, this is called a stator. And we talked a little bit about that in the vocabulary. It's electromagnetically charged. So it's what actually turns the rotor. These little things right here are ball bearings. They're silver plated ball bearings. So they use metal versus liquid. So liquid has the propensity to create gas, which we don't want, and metal does not. It's just more efficient. Just know that they're steel plated and very efficient. Okay, and that turns the rotor up to 3,000 RPM, which is just really cooking. Okay, and it's made of copper. Copper helps dissipate heat as well. Okay. So that's going to turn that anode about 3,000 RPMs a minute, okay? And the reason they do that is if we shot X-rays all day long onto that tungsten plate right here, we would end up cracking or breaking that plate. So they decided that it's best that be rotating, so it puts the heat on there equally and helps dissipate the heat a little bit better, okay? All right. Okay, so what else can I tell you about? So the anode stem, we talked about that. That's made of molybdenum, usually high melting point. Um, so we know that it's oil around the X-ray tube. Inside, we have no air whatsoever. Okay, and the metal housing is actually lead lined to help protect from X-ray, right? And we talked about the filament quite a bit, thermionic emission, that 99% of the electrons are converted to heat, where 1% are converted to X-ray photons. Okay, and one of these classes we will talk about the line principle, or line focus principle. It's pretty interesting. We will also talk about the anode hill effect, meaning that a lot of the X-rays are absorbed by the tungsten plate or the anode. So the X-rays on the anode side of the X-ray tube are going to be a little bit weaker than those on the cathode side. So if you have a person, you always want to put their biggest part on the cathode end of the X-ray tube. Okay. So I hope you guys kind of understand that. If you have any questions, please reach out. It's kind of cool that somebody was able to come up with this. It's actually really simple once you lay it out and see how it works. Okay, and I'm just going to run through it real quick, just in case you missed something. So electricity hits the generator. It hits the step-up generator, which produces more electricity, which comes into the cathode and heats the tungsten filament right here. The filament is heated to the point where it boils off negatively charged electrons into an electron cloud right here. And due to tube potential, is run across the tube to the anode plate, where it hits that anode plate and it's a rapid deceleration. And this is where electrons are produced into X-ray photons or heat. Okay, and these X-ray photons are actually directed down through a filtered collimator right here to help take away the weak electrons or the weak X-ray photons. And the ones that are emitted down to the patients are the strongest X-rays that we can produce. And the X-rays that are produced are either characteristic or Bremsstrahlung. And we need to know that Bremsstrahlung is the more common and the stronger of the two. Okay. The anode plate is actually turned by a rotor, which is powered by the stator magnetically. And there's steel plated ball bearings that actually help dissipate heat, as well as let the rotor turn freely and really fast. Okay, now the glass housing is actually surrounded by an oil to help dissipate heat. Okay, the metal lead lined capsule is the one we see when we look at our X-ray machine. Actually holds those X-rays behind, and if you shoot some big X-rays with a lot of mass and a lot of potential, you can actually go fill your tube and it actually feels warm. So there's a tremendous amount of heat that is produced in this process. So it's pretty cool. You know, you think about it, just pushing a button and an X-ray appears. But there's a lot of things that go on in that split second. It's pretty neat, actually. And this is something that you're going to need to be aware of for the test. There may be some questions about X-ray production and how exactly that it works. It's just important that you remember that the cathode is negative and the anode is positive. What the anode could or is made of, how heat is dissipated in the X-ray tube, how electrons are formed of the filament, the tungsten filament, and the percentages of electrons that are converted to heat and X-ray photons. So anyway, pretty cool stuff. Next week, we'll go a little bit further. And I hope to see you there. Anyway, this is just a little thing depicting why it's so important that we take two different views. The one on the left, which is the lateral, looks like that lion is eating her cub. And you look at the AP picture, and you can see that the lion is just carrying her cub. Okay, so that's the important part that we do in AP and lateral. Okay, well, I appreciate everybody being here today. I hope that this was helpful. If you have any questions about how x-rays are produced, please reach out. To me, it's fascinating, and I do like to talk about it. Anyway, I hope you guys have a great day, and I will be dropping a positioning video today on the Sterling Hub under the radiology group. It's actually the clavicle positioning, and one of my favorite things to shoot. I hope you enjoy it, and I hope you take those videos and use them and learn how to position really well. Anyway, I appreciate you guys being here, and I hope you have a great day. Okay, we'll talk to you later. Okay, guys, have a good day.